Monday, that certain things can go in and out of the lipid bilayer, and certain things need to go through proteins. And so we're going to talk about why things move in the first place. Why do they go into or out of the cell? Why do they move? And so the first type of transport across the membrane that we're going to talk about is passive. Passive means that it does not require an input of energy. So you don't have to put in any additional energy to get the substance to move. There are two types of passive transport that we're going to talk about, diffusion and osmosis. So diffusion is the passive movement, meaning it doesn't require an input of energy, of particles from an area of high to an area of low concentration. Osmosis is the diffusion or passive movement of water. So osmosis is the special name for water diffusing. And it says in response to a solute concentration gradient, a pressure gradient, or both. And as we go through, we'll talk about these and they'll become a little bit clearer. Okay. So diffusion could be across the cell membrane for things to go into or out of the cell, or it could be just in everyday life. So if I were to stand up here and I were to spray some perfume into the air, all right, with a perfume bottle. So I spray the perfume into the air. I would be able to smell it probably first, then who? Yeah, the people in the front. Would the people in the back and the corners eventually be able to smell it? Yeah, probably. Can somebody explain to me why that is? What is going on that allows a little bit more in depth than just saying it's going from a high to a low concentration? So what is actually going on to cause those molecules to move from one place to another? Jacob?
Movement of the air particles and pushing the perfume particles around and spreading them out.
That's exactly right. So what's in the air are gas molecules. Those molecules have a kinetic energy. They are moving around. What you are doing when you spray the perfume is you're spraying other molecules, perfume molecules, into the air. Those perfume molecules are in high concentration in this one area, but what happens is they're moving, the air molecules are moving, they bump into each other, and they spread out, and they ricochet off of one another, and so eventually they spread out, so they are going from a low to a high concentration, but the reason is because of that random movement. And so eventually those molecules will get to the noses of the people in the front row, and then eventually to the people in the corners and in the back. And eventually, no matter where you went into the room, you could smell the perfume molecules equally. They would spread around equally. Does that mean that they've stopped moving? No, they're still moving, but they're about equal concentration no matter where you're at in the room. That's an example of diffusion. So diffusion is totally due to the random movement of particles, okay? So is osmosis, movement of water. So this just shows you an example. This right here is a fake membrane. And so they're showing you, this is the membrane. And right here between this is the pore size. So right here, there are pores in the membrane. And what happens is molecules can move through those pores as long as they're small enough to get through the pores. So this is showing you two solutions, one with just pure water, one water with, let's say, food coloring in it, some dye particles. So we can see the particles in the molecules of dye within the water. And so what happens is if we're looking at just the movement of the dye, the dye molecules have a kinetic energy. They're moving, they're bouncing around. Some of them may hit the membrane and ricochet off, but if some randomly hit that pore and they're small enough to go through, they'll go to the other side. And that's what we see here. So now you have some molecules of dye on the other side. The molecules of dye are moving on both sides, but the higher concentration is over here. So these dye molecules, since there's a higher concentration of them, have a greater rate and a greater chance of then one of them hitting the pores and going over to the right-hand side. These guys here, there's a lower concentration of them. They're still bouncing around. They could, like this one here, hit the pore and move over to the left. But since there's a lesser concentration of them on the right-hand side, the chances of that happening are lesser than over here. So what you have is, if you notice here, you have more diffusion of the dye molecules left to right than you do right to left. So that's what's called net diffusion. We would say overall the dye is moving to the right. It doesn't mean that no dye molecules are going to the left, just the majority are going to the right, okay? And so then eventually it gets to equilibrium, and notice the arrows are going here in both directions. That's showing you that the dye molecules have not stopped moving. They still have kinetic energy. They still have a chance to hit those pores and therefore diffuse to the other side. It's just that because these guys are on in equal concentration, that the rate at which they hit the pores are the same, and so they would diffuse back and forth at equal rates because their concentrations are equal. All right, and so so this picture here shows you it's this. This picture is this right here with the orangish yellow dye, just adding the purple dye. So they're just showing you here that two dyes or two types of molecules on opposite sides of the membrane will diffuse independently of one another. So the same thing is going on as the last picture with the yellow, but the purple ones, the high concentration starts on the right, and they're going to do the same thing. They're going to randomly bounce and hit the pores and eventually diffuse to the left side until we reach equilibrium. So they're both diffusing independently of one another until equilibrium is reached and there's equal concentrations of either dye at either side of that membrane. So molecules will always diffuse to equilibrium if it's possible. A situation where it wouldn't be possible is if the pores were too small and the dye couldn't get through. Then you could never reach equilibrium there. All right, so that's with diffusion. Diffusion, we looked at molecules of dye. Osmosis is the special form of diffusion given to the diffusion of water. That name is given to just the diffusion of water. So let's look at what you're seeing here. So let's just look at this upper left-hand U-shaped tube. So here, the two solutions on either side are separated by a selectively permeable membrane. So that means it only allows certain things to go into or out of it. So it tells you what it allows through. So sugar molecules cannot pass through the pores, but water molecules can. So water molecules are much smaller than the sugar molecules. The water molecules can get through the pores, the sugar cannot. And these little green dots here are the sugar molecules. Now, what they're trying to show you with the level of water, they're showing you the molecules of sugar, just the blue here is the water molecules. They're not showing you individual water molecules. But notice the levels of water are the same. And so, they're trying to show you that there's the same number of water molecules on the left and the right. The difference is the number of sugar molecules. There's less sugar molecules over here than over here. So therefore the lower concentration of solute, higher concentration of solute. Let me ask you this, what side, the left or the right on this picture here, is the higher water concentration? It says the solute concentration. So it would be what? The left. And so we would have a higher water concentration over here. I know that because it says it's a lower solute concentration. So therefore, if I were to figure out percentages of the solution, this solution has a higher percentage of water than this solution over here. And so over here, we have a lower concentration of water. And things always diffuse from an area of what to what concentration? High to low, and that's why it's showing you water will then diffuse, because it's going from high to low concentration, and also because it can get through the pores of that membrane. So if we look at here afterwards, we would see then the level of solution going up because water is diffusing to the right. What this picture down here is showing you why it will go from high to low concentration and go from the left to the right. So if we look at this, this is showing you the individual water molecules. So right here, this is just blue. We can't see the individual water molecules. Here we can. And here's that little bit of sugar, half of that sugar molecule showing you here. Here we have 3 sugar molecules that we can see because the right-hand side has a higher concentration of sugar molecules. So what's going on here is, if you remember when something dissolves in water, what water does is it adheres to it and forms a hydration shell. The water surrounds it. Do you guys remember that from chapter 3? So when you have a lot of sugar, like this side here has more sugar molecules, a lot of the water molecules over here, you might have the same number of water molecules. Let's say we have 100 water molecules here and 100 water molecules here. You have the same number of water molecules. The concentration, though, is different because there's more sugar over here. And so out of those 100 water molecules, these water molecules are binding and surrounding your solutes, your sugar, which means then that a lot of them are tied up in dissolving the sugar, and there's less free floating around, versus on the other side, there's less sugar molecules. And so what happens is these the water molecules are still forming a hydration shell and bonding to the sugar molecules, but since there's so many, less of those sugar molecules, there's more water molecules that are free, not dissolving the water, that these water molecules can bounce around, and since there's a greater number of them not surrounding the sugar, then they can hit the membrane and diffuse over to the right-hand side. There's very few of them free over here, so the chances of them, those few free molecules bouncing around and hitting the pores are less. So therefore, you have more water moving from left to right than you do right to left. All right, and so that's why having more sugar decreases the concentration and therefore ties up those water molecules so that they can't diffuse. So our overall diffusion is left to right, even though we have some going over to the left, and that's why it increases there. And eventually it will diffuse until equilibrium is reached, where you get the same sugar concentration. So that is osmosis. So when looking at different situations of which osmosis can occur, there's some vocabulary in terms of solutions that I want to introduce to you. When there's no difference in concentration between a cell and the surrounding solution, the cell is said to be in an isotonic, or sometimes called isoosmotic solution, and therefore there's no net. Again, no, that doesn't mean there's no movement, but no net movement of water or particles. And so an example of what a cell would look like this in an isotonic situation is, if this is your cell, if the outside of the cell is 80% water, let's say, and the inside of the cell is 80% water, it has the same concentration of water, and let's say it's 20% solute. Solute's just generic term of anything that's dissolved in that water. So that equals 100% of that solution, and this is also 20% solutes. So when we look at, when it says here, no net movement of water or particles, the water will still move out and in, but because the concentration of water is equal, inside and out, and therefore the concentration of solutes, water will move equally into and out. So for every one that diffuses in, one will diffuse out, and you will get no net like size change or anything like that with the cell. So we say that these two solutions, so if we call this solution A and solution B, these solutions are isotonic to one another. All right, and we would say then the cell is an isotonic solution. But let's look at what happens when cells are placed in solutions that are different than the cytoplasm inside the cell. And remember, some membranes are selectively permeable, so we're going to let the water, we're going to talk about water going in and out here. So on the next two slides, we're going to just, for simplistic sake, just like I did here, we're going to assume that only water is allowed to cross the membrane. So like this one, I focus just on the movement of water. It gets a little bit more complex as we look at solutes as well. We'll eventually do that, but yes.
Would that be considered equilibrium?
Yes. Yes.
And so even when you do reach equilibrium, the particles still move evenly? That's right. So they never stop.
They never stop. Yeah, absolutely. Okay. So the outside solution is different than the cell. There's a solution that we call hypotonic. Do you guys remember these words? Isotonic, hypotonic. A little bit vaguely. Somewhere back in the sources of your brain, a little bit. A cell that's placed in what we call a hypotonic or hypoosmotic solution will swell and burst. A solution that's hypotonic to the cell is less concentrated than the cell. In other words, the cell has more stuff or solute particles inside relative to the surrounding solution. And so what will happen is water will flow into the cell and try and equalize the concentration difference. But if there's too much of a difference and too much water flows into the cell could actually burst before equilibrium is actually reached. So with a hypotonic solution, let's do the same type of thing that we just did here with the isotonic solution. So here's your cell, and let's do the same percentages inside the cell. So that 80% water, 20% solutes. What I'd like you to do is to write example percentages that would have to be true about the outside of the cell, the solution on the outside of the cell, to cause that solution to be hypotonic. Example percentages. So you are putting an example of what percent water, what percent solutes would the outside need to have in order for that outside to be hypotonic. So let's look at this. So it tells us when the cell is placed in a hypotonic solution, water is going to flow into the cell and could burst. So we know water is going to go in. That's the direction in which water is going to flow. So what would have to be true about this percentage of water compared to the inside, Megan? It needs to be higher than 80%. It doesn't matter what number you put in here, as long as it's higher than 80. So it could be 81%. All right. So I'll just put 90% water, and then that would mean it would be 10% solute, and it would go in, and from high to low concentration. All right. And so that is a hypotonic solution. I want to look at the next one, which is hypertonic. Cell placed in a hypertonic or hypoosmotic solution actually shrinks. A solution that's hypertonic to the cell is more concentrated than the cell. In other words, the cell has less stuff or solute particles inside relative to the surrounding solution. So in this case, water is going to flow out of the cell and still try to equalize that concentration difference. So hypertonic solution, go ahead and draw yourself a cell, put example percentages inside and out of the cell to show example water and solute percentages that this would be the case. That would cause the outside to be hypertonic. So if I I kept that inside the cell as 80-20. Water, it says, flows out of the cell when a cell is placed in hypertonic solution. So water is going to diffuse out, so therefore the percentage of water should be lower, right, than, so I could do 75. It doesn't have to be much lower, all right, and then I get 25, all right. And so that is your hypertonic solution. I do want to point out, when you use the words hypo and hypertonic, you cannot use that when you only have one solution. So if I had a beaker of a salt solution here, I couldn't go, ooh, that solution is hypertonic. Why? Because you can only use those words in comparing two solutions. So you have to compare the two solutions and to tell if it is hypertonic or not, compared to the, in this case here, the outside solution to the inside solution. So outside here, we said that the outside is hypotonic. It has less solutes in it. So if we were to take it from the direction of looking at the inside solution compared to the outside solution, the inside solution we would say is hypertonic compared to the outside solution, okay? So water, if you notice here, will flow from a hypo to a hypertonic solution, all right? Hypo has high concentration of water, hyper, lower concentration of water, higher concentration of solutes. And so then if we look at here, this outside was a hypertonic solution, lower concentration of water. This would be hypo compared to the outside, and therefore water flows from a hypo to a hypertonic solution. All right, and so, in using these words, I use them in terms of the solution that it's immersed in. But if I asked you what is the cell compared to the outside, you would say here hypertonic. The solution on the outside, you would say it's hypotonic to the solution on the inside. Okay, and so that's how you use those words. So, so now that sheet that I asked you to get out, the osmosis practice sheet with my writing, I'm gonna have you actually do these right now as little practice problems, and then on the flip side of that, let me explain the opposite side. So flip this one right here. All right, flip it over, and let me explain that sheet. You have a picture, and this is a picture that I actually whited out. There were some words on there, and I whited them out. You can see where my whiteout was a little bit, because I wanted you to think through it. And so up here I put what I want you to do. So on that side that says water balance of living things, first of all, notice it's set up like a chart. So you have 3 columns for different types of solutions. So iso, hyper, and hypotonic solutions. And then you have 2 rows to show the plant and an animal cell immersed in each one of those 3 different kinds of solutions. So on the sheet, what I want you to do is label the solution that they're immersed in. So notice at the top of each column, I whited out as blank solution. So you're going to put what the cell is immersed in, what kind of solution. Draw arrows to show where the water is moving, and put example percentages to show why water moves in the direction you said it would. And then after you finish that, looking at that, I want you to look at the plant and animal cells in the different solutions, and I want you to think about which situation would be ideal for an animal cell. So what's an ideal solution for an animal cell to be bathed in and a plant cell to be bathed in? All right, and think about why that is. Okay, so I'm going to give you a few minutes to do that. Pause the video here. Okay, so let's go over this together. Okay, guys, so for this first one, get my markers here. So you have salt, you're only given percentages of salt inside and outside, and it's asking you where the water you can figure out the percentage of water, and that is the difference in that they equal 100. So therefore, we should have 88% water on the outside and 82% water on the inside. So therefore, water moves from high to low concentration, so water would go into the cell. So then B, where will the salt move? So salt, provided it can get through the membrane, so salt would also move from high to low concentration. So salt would move out of the cell. And they would continue to do that until equilibrium was reached, and then they would go into and out of the cell at equal rates. All right, what's that? And so then it asks you which solution is hypertonic and which is hypotonic. So comparing these two, they're not isotonic because they're not equal. And so which one is hypertonic? Hypertonic. Yep.
The one inside the cell.
The one inside the cell. So this is hypertonic. And this is hypo. Whenever you have a hypotonic solution, you have to have a hyper. And remember, water moves from hypo to hyper. All right, number 2 asks you to draw a cell in an isotonic solution, show the concentrations. So it doesn't matter what you put in terms of percentages as long as they're the same. So you could do like 75% water on the inside, 75% water on the outside, and then whatever solutes would be 25%, as long as the solute, which is in general. And therefore, we have no net water or solute movement, but if the water can get through the membrane, they're diffusing, remember, at equal rates. All right, so then this picture here, this picture, we haven't talked yet about dialysis tubing. We're going to do a lab with diffusion and osmosis, and we're going to make fake little cells out of something called dialysis tubing. If you've had anatomy, that's probably the only place that you probably have used dialysis tubing before. But what it is you can, it's a tubing that you can put solutions in and tie off either end, and it acts as a fake cell because it's used for this because it actually has pores in it of a certain size. And so as long as molecules that are small enough to get through the pores can get into and out of the cell through these pores. So it kind of acts like a selectively permeable membrane. It's selectively permeable but based on size only. All right, so and so this is a little fake cell inside here. So write an example of solvent concentrations both inside and outside the cell to show that the solution outside the cell is hypotonic. So we want hypotonic on the outside of the cell. That means where's the higher water concentration going to be? Outside the cell. So we have a higher concentration. Whatever you put here, the water concentration needs to be higher than what it is on the inside of the cell. So I'll put 70. That means then you have 20% solutes and 30% solutes. And so water would go where? Water would go into the cell. All right? And that would mean the inside of the cell, what would we call that solution? Hypertonic. This is hypotonic. Inside the cell is hypertonic. And then lastly for this one, when the concentrations on either side of the membrane become equal, what do we call it? That is equilibrium. And do the atoms and molecules stop diffusing? Absolutely not. So they just diffuse at equal rates. So the concentration. All right. So if you look at the backside, so you had to label the solutions. But first of all, let's just look at the pictures here. So let's look at this column on the left. And so if you look at the pictures of the animal and plant cell, where do you presume water is moving? Into or out of the cell? Into. This, if you look at compared, let's just look at this animal cell compared to these two cells here. It looks kind of shriveled up. So therefore, water is actually moving out of the cell there. And so that will be the case here as well. All right, the same thing's happening with both of them. And so then I asked you to put example percentages that would cause that to happen. So no matter what, you have to have a higher percentage of water on the inside of the cell. So we could do 90% water inside, 80% water outside, or whatever you use, as long as your water is higher on the inside than the outside, and then your solutes would be higher on the outside. So water's going out. This percentages would be the same as down here as well. So the outside, we would say this cell is bathed in a what kind of solution? So what should I put up here, outside here? This is hypertonic, which means the inside would be hypo. And so we'd say that this is bathed in a hypotonic solution. The inside would be hypo. All right, and then the exact same thing is going on with the plant cell. But let's take a look at the animal cell shrivels up. And that makes sense because as water's leaving, you have less stuff in the cell, so it's not going to take up as much space because there's less matter, and so then the cell membrane kind of shrivels up because there's not as much stuff inside the cell. Same thing is happening with the plant cell, but the plant cell looks a little bit different here. First of all, the plant cell is not shriveling. Why? Because it has what? What do plant cells have?
The cell wall.
The cell wall. So this right here is this is the cell wall. And the cell wall is pretty rigid, and it is not going to shrivel up. So therefore, the plant cell kind of maintains a little bit of its shape. Now, notice what's happening here. You see this part here. What's right underneath the cell wall in the plant cell? The cell membrane. So let me draw a normal plant cell. Remember, this is the cell wall. Cell membrane's right underneath it. And then normally we have, remember what's the big thing that holds water? The central vacuole that holds some water. And also there's water in the cytoplasm as well, and so on. And so what happens is normally, when the plant cell has water, the central vacuole is filled up, there's a lot of water in the cytoplasm, and it's putting pressure against the cell membrane, and the cell membrane butts up right against the cell wall. But what happens is that when a cell is placed in a solution that has a lower concentration of water, this water is leaving, and the water leaves the cytoplasm, but also the central vacuole. This right here is the central vacuole. Notice, compared to the other plant cells, this is the central vacuole bigger here. This is much smaller, and that's because water is leaving the plant cell through via the central vacuole as well as the cytoplasm. That means then there's less stuff inside the cell, and there's not as much pressure to put on the cell membrane. And so what happens is this right here, I made the cell membrane red here. I'm going to outline the cell membrane here in red. This is actually the cell membrane, and it's kind of shriveling up and shrinking away from the cell wall. And so all of this right here is the cell membrane like that. And so I'm going to write here that this is the cell membrane shrinking away from the cell wall. And that's because the volume of water that's leaving. The water is leaving, and therefore, so this is kind of, this white spots here is kind of like empty space. It has gases, and so it's not a vacuum, but it has gases and things like that in it. But the cell wall and the cell membrane are kind of separated a little bit here. And so that is, if you see plant cells that look like this, that means that it has lost water because it has been put in a hypertonic solution. All right? And so it's a little bit different between plant and animal cells. So then let's look at the next solution. So this is hypertonic. So this solution either needs to be iso or hypotonic. Which one is it? This one is isotonic. So what does that mean? If the cell is put in an isotonic solution, the concentrations are equal, and the solution outside the cell than inside the cell. So whatever percentage you put of water outside So water is going to go in and out at equal rates. Notice here, the cell membrane, you have, the cell membrane is now against, so I'll put red here. The cell membrane is against the cell wall. That's because it's not losing a bunch of water here. So it's putting some pressure against the cell wall. Alright, and so that leaves the last one as hypotonic. And so that means the outside, when we talk about this, the outside is hypotonic to the inside, so the inside is hypertonic. So in this case here, water is moving where? Into the cell, right? Water is moving into the cell, and why? Because you have your greater concentration of water outside, so 90 versus 70, let's say. So water is going into the cell, 10% volume, it's here, 30%. So you did that right if your percentage is greater water on the outside than the inside. Water goes in. Now animal cells, their outermost part is the cell membrane. Remember, the cell membrane has the consistency of salad oil. So as water goes in, if there's a great enough difference between the percentages, remember it's trying to get to equilibrium, and if too much water goes in, it puts pressure on that cell membrane, and that cell membrane is not very strong, and it lyses or gets holes in it, and the cell bursts, which clearly is not good for the cell because the cell dies. All right, and so that's not a good situation there. But let's look at the same thing in terms of water is going on with the plant cell. Water is going in for the same reason that it went into the animal cells. But look at the plant cells do not burst. Why? Because of the cell wall. So notice here, if you compare this picture to this picture, the cell wall is kind of ballooned out a little bit. All right, and that's because as water goes in, remember it's putting pressure and pushing the cell membrane against the cell wall, but it never bursts because that cell wall will put pressure back against it, and so therefore will not allow it to burst. Now, looking at these three situations for animal cells, what's the ideal situation for an animal cell, you think, to be bathed in what kind of solution? Yeah, this is ideal here for an animal cell. And our cells are bathed in isotonic solution. Our cells are bathed in extracellular fluid that's isotonic to our cells. Our cells are not bathed in blood. People think that cells are bathed in blood. Blood is solely contained in your blood vessels. It doesn't touch your cells. Your cells are bathed in another fluid called the extracellular fluid, and it's isotonic to your cells. That way, neither one of these extremes happen to our cells. What about plant cells? What should be the ideal situation for plant cells? This is ideal for plant cells. Because remember, water, when it's filled to the max for plant cells, it makes it very, very sturdy and stands up nice and straight and helps to give support to the plant. If plant cells are in an isotonic solution, they actually balloon a little bit. All right? So they need that pressure inside to stand up properly. All right? So that diffusion that you change to diffusion osmosis here it says as
we're going with
Dialysis tubing sounds pretty cool.
They come here. I think it's still recording.
Oh.
Yeah, it is. 40 minutes.
You think that'll
Good lecture today.
You think that'll end up?
No. So edit it out.
You never know.
I'm going to stop this video.